Welcome back. So last time I asked you to calculate how much energy would 2 billion people, each using one 50-watt light bulb, require. Well, it's a pretty simple mathematical question, right? You simply take 50 watts times those 2 billion people. And what you find is that you have 100,000, if you prefer, watts, or in reality, that's 100 gigawatts, or 100 times 10 to the 9 watts of power, if each individual in their lifetime only uses one light bulb. Well, we know that's not realistic, right? We know that the energy demands will in fact be much higher than that. And so we know that we're going to need a lot of new power. And it may be nuclear power plants, it may be something else. We're going to discuss, scale and perspective so we can see how we can meet in a thoughtful way this increased energy demand. That's what we'll cover in this class. So let's talk about where we are now and how that might change. So here we have global consumption of energy by source. The energy type here is listed in quad BTU, a little bit of a strange unit here, a British unit, a British thermal unit, which is a unit of energy. And the quad is a multiplier of 1 times 10 to the 15. What we have here is the years from 1980 to 2004. And these are data that I extracted from the U.S. Energy Information Administration database. These data are freely available again to the public, and the EIA website is in fact very informative. Lots of really great information on solar energy, wind energy, fossil fuels. So I highly encourage you to explore their website. It's lots of good data. And so what I wanted to show you is essentially the energy portfolio in the world today and how it's been changing as a function of time. And the red represents the energy generation by petroleum, green is natural gas, blue is coal, pink is hydroelectric, and yellow is nuclear. And this tiny sliver right here, which the spreadsheet tells me the color cyan, are renewables. And so what we can see is that coal, natural gas, and petroleum, or the fossil fuels, dominate the energy portfolio. Over 85% of the global energy supply is provided by fossil fuels. And if we look at these numbers, again, recognizing that this is a huge multiplier, we can see that there is a steady increase in the overall demand for energy, and that is a lot of energy. So any shift in this portfolio requires that we have scale and capacity. So in other words, if we want to just displace, let's say, 15% of the coal, that will require that we have a lot of capability that can be used to replace the coal. So take, for example, the renewables, which in this categorization represents geothermal, solar, wind, wood, and waste electric power. So this is like biomass or other materials that are being burned, are all lumped into this category of renewables. If we double the renewables based on these 2004 data, we wouldn't see a significant impact on any of the fossil fuel sectors. Triple, nope. Order of magnitude, getting there. Now, admittedly, these data are circa 2004. Since 2008, there's been a significant increase in the use of renewables around the world. So these numbers have shifted some. But the point is, a lot of energy is being generated using fossil fuels right now. And if we want to shift that portfolio, we need to have technologies that are capable of scaling. Okay, units are absolutely critical for thermodynamics. They're actually very helpful to us, and sometimes they can be hard in terms of our understanding and being flexible. So common units and conversion factors for energy analysis are provided on this slide and the next slide. And we're going to start with a discussion of pressure, which has a lot of different units that are commonly used. In SI units, Pascal is the appropriate measure for pressure, but we'll often see bar or atmosphere are also very common in this community, or PSI. The A here designates whether or not it's absolute. You also say PSIG, which is pressure on a gauge basis, which is relative to a reference frame. And the texts that we have for our class go into a good discussion of the different units and the different conversion factors. So I encourage you to explore that background material. But we should be flexible in being able to move from one unit to another. So if I give you a question and the units are in Pascal, you should be able to convert those into whatever unit is the most appropriate for the analysis, and which is the most convenient for you, that you have the strongest connection to and the best familiarity with. Energy also has a huge range of units that we can see here. For example, we have joules, which are the units for the SI community. BTU are the British thermal units that I mentioned before. Kilocalories are what's used typically in the combustion community or in the chemistry community. The chemistry community will also use electron volts if they're working on per molecule type nuclear reactions. The commodities community will use MTOs or BOEs, which are million tons of oil equivalent. The point is that while from an engineering standpoint, we always want to use our SI units, and we've been trying to standardize with SI, in reality, there are a lot of communities that have tradition associated with them of using particular units, like, for example, the commodities industry would prefer to work in tons of oil equivalent. So we need to be flexible, and we need to be able to recognize when a unit is a unit of energy, or, for example, when a unit is a unit of power. So on this slide, we can see the units for power, which is the energy rate, or the energy per unit time basis. And again, for SI, that's a watt or a joule per second. And we can also see sometimes a watt will have a subscript associated with it in terms of whether or not it's a watt of electric power or a watt of thermal power. So subscript designates essentially whether this is a thermodynamic calculation, which is the watt of thermal power, and when do we include the effects of the conversion efficiencies from translating thermal power into electrical power. So for example, if we want to include the efficiencies of the generator in converting shaft power to grid power. And again, all of the units that we saw before for energy we'll also see on a rate basis. And again, different communities have different traditions. And you'll see things like horsepower, for example, is really the standard that's used in the automotive sector. So ton is a cooling capacity. That's a unit that's used in the HVAC, or the heating, ventilation, and air conditioning sector. So again, we have to be flexible and we have to be smart. We have to be able to use different units. We have to be able to convert from different units. And we have to be able to recognize units when we see them as being energy units, pressure units, power units, things like that. Energy density is vitally important for the transportation sector. And that's when we take that energy and we say, well, how much energy can I get from that system on a per mass basis? So we often use that as an energy density per mass. Sometimes we'll see it as a per mole basis. Sometimes we'll see it as a unit area. We won't do that in this class, but that's often referred to as an energy flux as opposed to an energy density. And again, if it's an energy density and it's normalized per unit mass, you're going to have units of kilojoules per kilogram, for example, if you're using SI units, BTU per pound mass, for example, if you're using British units. So again, those examples are provided here. But any of the units we had before for energy can be normalized by mass or mole and expressed on an energy density basis. So again, we have to be smart and flexible. Prefixes, which I'm sure many of you are familiar with, we mentioned before, our increase in power based on population was going to require 100 gigawatts of new power. Well, that's 1 times 10 to the 9 watts. And we talked about quad BTU, which was the global energy demand, was about 100, on the order of hundreds of quads of BTU. Well, that's 1 times 10 to the 15 BTU. So again, we have to understand what these prefixes mean, and we have to be able to convert between them. So my family of kind of SI units here, my family of assorted British and other units here. Okay, now that we've had a discussion of units, then hopefully these graphs make a little bit more sense. This is quad BTU, so we now know that's an energy unit times 10 to the 15 power. This is U.S. sources of energy based on the different sectors, energy carriers. And here we can see petroleum is in black, natural gas is in red, coal is in blue, and nuclear electric power is in light blue here, dark blue for coal, and hydroelectric is shown here in green. And we can see that this distribution, if we wanted to convert it into a bar chart like I presented in the previous global distribution, is just about the same, right? The fossil fuels dominate the power generation in the United States. Nuclear is about 20%, a little less than 20% of the overall portfolio. And biomass here, which includes some of the renewables, and hydroelectric represent a very small fraction of the overall distribution of energy carriers in the United States. So one of the conclusions we can make just by looking at this graph is, again, if we doubled renewables, well, that'll have an impact, and a good impact, and it is something we should do, but it's not going to displace a significant amount of the fossil fuels. So while we're working on efforts to increase the diversity of the energy portfolio to include smart and thoughtful renewables, we should also work on improving the combustion of fossil fuels, because imagine a 25% improvement in fuel economy. That can have a very dramatic impact on reducing carbon emissions and on reducing petroleum use. Now that's tricky, and we'll discuss why that's hard to do, why it's hard to achieve 25% fuel economy improvements and things like that in this class. But we need to be working on essentially all of those issues simultaneously. And not only improving efficiencies, waste heat recovery, all sorts of good things we'll discuss, but we also need to look thoughtfully at how we can reduce consumption overall. So conservation measures have potential to have considerable impact. Okay, so now let's look at energy supply and demand by sector in the United States. Now the supply side is shown here, and this is a graph out of the Department of Energy, again out of the EIA office at the United States. So they have some really nice graphics to kind of quantify, show you visually what's going on in terms of energy supply and demand. On the supply side, we have the fossil fuels, and they've been divided into domestic production and imports here, but the same suspects appear, right? Coal, natural gas, and oil. On the right-hand side, this is our demand, and these are broken up into different sectors: the residential, commercial, and industrial, and transportation sectors specifically. And there are some units here that are assigned in terms of these production and all these different energy supply and demand vectors, but we don't need to know the specifics of the specifics of the units. Let's just say we have some 100% here of consumption. And if we look at the amounts of energy that are used in residential, commercial, industrial, and transportation sectors, we see that, well, it's almost roughly about 25% in each sector. A little less in residential, a little more in industrial, a little less in commercial. But there isn't an outlier. There isn't one area that is an energy hog. So then we have to think about, what are the energy demands within the sector? What do we use energy for in the house? What do we use it for in industry? And what do we use it for in transportation? So what I want you to think about is all those examples of each of the different energy sectors, and which of those energy sectors do you think has the most demanding requirements for transient energy? So that's energy provided on a time-varying basis, so energy that changes as a function of time. So out of those four sectors, residential, industrial, commercial, and transportation, which sector has the most challenging demands for transient energy supply? And that's where we'll start next time.